Hello everyone, this is Mark again. Before we start today's technical content, I would like to mention that my videos are not a direct replacement of your lecture. In fact, my videos are under the assumption that you have already went to your lecture and understood the basics of the content, and then perhaps you may have even done some homework questions and then would like to get a deeper understanding and even get ahead of yourself to prepare for the exam a little bit. So with that said, let's go ahead and start with today's content, which is lines and planes in 3D, right? And we will start with quick questions as usual, right? So this is sort of the basic definition problem, right? So we have three different types of expressions, and I hope everybody understood you are looking at an equation of a line, right? But there are three different ways of you can represent a line, and then they have their own unique names, which are hidden behind the space shuttles. So I want you to think about which is which, because you will likely encounter them on your homework and on your exams. Okay, so I assume you have paused the video and thought about it, and here are the answers, right? So the first one is vector form. So vector form is pretty easy to understand, right? So you have your point, right? Your point and your vector, and then the vector is parameterized by your parameterization variable t. So it's written in because the reason that it's got a vector, the name of the vector form is because, well, you have vectors, right? Oh, so actually, this is not a, this is a point. I mean, I think in the definition of MA261, a point should be defined as curly brackets, and then that's the notation I will use going forward, rather than these sharp ones, the carets. Okay. And then the parametric form is written in the way that you have these parameters, right? Your parameterization variables showing up in each equation, right? And each equation is the x component, y component, z component coordinate of your line. And lastly, it's symmetric form, right? A symmetric form is just named after the look of the equation themselves, right? It looks pretty symmetric to me, right? Especially, with this axis. And if you can put everything, you can actually put another equal sign behind it, and then that will equal to your t, your parameterization variable. And if you rearrange all of this, you will get the exact same thing as the parametric form and then the vector form. Okay, so that's on the comments of equations of planes, lines. So next we'll talk about, I want you to think about how and why a vector and a point can define a line or a plane. Okay? And this is one of the fundamental things that you need to understand in this lecture. Okay, I hope you thought about it, and I'm gonna go ahead and pull up my notes. So let me go ahead and then use this as an example. So a line, a point and a vector, okay? A point and a vector. How does that define a plane to start with? So I think this is a relatively easy question to answer because, well, if we look at this diagram, the diagram on the left, on the left, right? So you have your starting point, and then you have the vector that's pointing in the direction of the line. So you have a starting point, and then you have your direction, and then how far you go, it's determined by your parameterization variable t, right? That scales that direction vector to your destination, right? T times the vector. So a point and a vector can define a line. Well, what about a plane, right? So let's go ahead and scroll down, right? So So this is an interesting question. So the point is any point that lies inside the plane, right? So the PO is laying flat inside this plane, okay? And then that's the point. The vector, it's not just any vector. It has to be the normal vector, the vector that's perpendicular to the plane, right? You can be pointing upward, you can be pointing downward, but it has to be pointing normal to the plane. And these 2 points together can define a unique plane in the 3D space. Okay? I hope that clears something up. And then we will use this concept a lot in our questions. And then, so this one, I want to save this later on, and then I want you to thinking about this question a little bit, and then we will talk about that in detail, using an example to illustrate that. So, and another question I want you to think about is, how do you know whether 2 lines will intersect or collide? So I hope you understand the difference between intersecting and colliding. So think about that. Okay. So intersection is that it's 2 lines that is, let's use the example. Let's say we have a crossroad, right? We have a crossroad, or this is a bad crossroad. Let's use crossroad like that, right? So we have 2 cars, right? One going this way, one going that way, right? These are representing our lines. And if they intersect, right, by definition, right, an intersection is, 2 lines intersecting themselves. But so that means they will come across at the same point in the space. But what separates intersection from colliding is that colliding, you need to have, let's say we have 2 cars, right? Let's say unfortunately we have a car accident. That means 2 cars reached the same point at the same time, right? The key is that at the same time. Okay? So that's the difference between intersecting and colliding. And then let's start with our main questions. All right, let's take a look at the first question. This is from exam 1 for 2018. Okay, I have where I got this question from labeled down at the bottom right. So given 2 planes, which our equations are here, which equation describes the parametric equation of the line of intersection of 2 planes? So I'll let you think about it. Especially I want you to think about what are some of the solving steps, right? This is the process that we can take to arrive the equation. Okay, so let's take a look at what I have here. So this is the one pager that I have created that will help you identify the type of question by looking at the keywords, because one of the challenges in this class is there will be many topics and related types of questions that you will be encounter. And then one of the things that you need to do and do well in your exam is to identify what type of question you're looking at. And the best way to do that is by looking at the keywords. So once we know what type of question it is, we will utilize the solving steps that I have created below, which we will go into. These are the steps written in English that are easy enough for you to take each step, right? I break this big question into smaller pieces so that you can, gradually arrive to this question. And these are like very easy things to do each step. Okay, so let's review the question, right? by reading this question prompt again, right? Given two planes, right? They gave you the equations, and they want you to find the equation that describes the intersection line of the planes. So this is an intersection line of two planes problem, and then in this case, the keywords are very easy to get, right? Like this is basic, right? They ask you, they will tell you explicitly what they want, right? So we have planes, you have intersecting line, right? So the first step I would start is by finding the normal vectors, of the planes v1 and v2, right? Let's go back and then look at these equations of the planes, right? So I have the first step, right? v1 and then v2 equals to, right? Oh, sorry, my bad. v1, the 1, 1, 1, I got them from the coefficients of the xyz, right? So xyz is 1, 1, 1. So v1 is 1, 1, and 1. So v2 is the same thing, right? So the coefficient in front of x is 1. The coefficient in front of y is -2. And then the coefficient of in front of z is 2, right? So that's my step number 1. Okay, step number 2 is I will find the normal vector, right? The normal vector, which is v1 cross v2. And this vector is important is because this is the vector that is parallel to the intersecting line, okay? And then I can, I don't know if I have my notes here to show you what that looks like. Yeah, so this is sort of my attempt to draw that out. So this is the vector that we can find by taking the normal vector of the planes, okay? So let's return to our step number 2. So step number 2 is, Vn equals to V1 cross with V2, right? So this is our first cross product that we will be computing together. So what we will do is we put the unit vector of the coordinate axes, right? I hat, j hat, and the k hat. And then we have the components of v1, 1, 1, 1, and then v2, 1, -2, 2. Okay? I'm going to make it a little bit more compact right here. So the way I compute the normal the cross product is I'm going to start with drawing these smaller matrices as your professor might have taught you, and you have I hat, right? So I'm computing my I components. So once I compute I component, I am going to sort of starting with my I hat, I'm going to draw a vertical line. I'm going to hide everything below it. I'm also going to hide everything across it. So what I left is 1, 1, and -2, 2. So I have 1, 1, -2, 2. And then I'm going to put a minus sign, okay? So the J component is always minus. It's a minus sign in front of it. And don't you ever forget about that. And then, so I'm going to apply the same technique, right? I'm going to start with J. I'm going to hide everything up across it. I'm going to hide everything up below it. So I'm left with 1, 1, 1, 2. And that's my J hat. And then I put a plus, right? It's plus, minus, plus. And then I have the final one, right? I'm going to have cross out my K of everything across it, everything below it. Oh, so actually I'm missing something right here. That's a 1. So that's 1, 1, 1, minus 2. And that's my K hat. Okay? So now I'm just going to compute these things really quickly for you. So I'm going to have... So what I'm going to do is... so for these the smaller determinants, what I'm going to do is I'm going to sort of look these 4 numbers in this pattern. So I'm going to start with 1 and then go to 2. So I multiply them together, right? So if when my red line is going down first, going from left to right and going down is 1 times 2, right? And then I'm going to circle back to go to 1 and minus 2. When I circle back, that's what I'm going to minus everything with. So that's minus 1 times -2, okay? So I hope you get this, what I'm trying to get at, right? So I'm gonna put in, and that's my I hat, and I'm gonna minus, so I'm going this way, so 1 times 2, so 1 times 2, and I'm circle back to look at -1 times 1, and that's my j hat, plus, right, I'm gonna go a bit faster, -2, 1 times -2, minus 1 times 1, okay? And that's my k hat. And this will give me a vector is 4, -1, and -3, okay? So this is the normal vector that's parallel to the intersecting line. So again, we have talked about that to define a line, we need a point and a vector, and we have found the vector. So now we need is to find the line, sorry, to find the point. So I'm gonna do that. So to find a line, the point, we're going to talk about step 3, right? We're going to create a system of equation, that's what SOE stands for, from the equation of the planes, right? So this is my equation of the plane number 1, and this is my equation of plane number 2. So in this case, we're going to write down the equation of the plane again, x plus y plus z equals to 1, and then x minus 2y plus 2z equals to 4. I'm going to separate this a little bit. Separate them a little bit. Okay, step number 3. So, and then we're going to set them up. So this is the system of equations, but look at how many equations, how many unknowns do we have, right? We have 2 equations and 3 unknowns, right? We have infinite many of solutions, and that's not going to be helpful. So to solve this equation, I'm going to make a crazy assumption that this plane, this line is not level to any of the x-axis, y-axis, z-axis. And why can I make this bold assumption, right? Look at the direction of vector of the line, right? It's not level, right? You can see that this is clearly not level to any of these coordinate axes. So why am I talking about this line not being level? Well, if it's not level, then at some point in time, right, if I stretch this far enough, right, stretch this line far enough from in one way or the other, it's going to hit the xy plane, right? So that's going to help me because I can set z equals to 0, and I can solve for the system equations now for x and y, right? Because I know that this line is going to intersect xy plane, which is z equals to 0 at some point, and I can set that for the and I can solve for the x and y coordinates when it intersects the xy plane. So we're going to set z equals to 0. So what we're going to end up with is x plus y equals to 1, and then x minus 2y equals to 4, right? This is a very easy system of equations. So I'm going to jump right to the solutions. We will have x equals to 2, and then y equals to minus 1. Of course, we're going to have, z equals to 0, right? So we're going to say z equals to 0. Okay, so step 5, now we can assemble the point of the line intersecting the xy plane, right? So step number 5, we were going to have the point equals to right, 2 minus 1, and then z equals to 0, right? So 2 minus 1, 0. So now we have the vector, and we have the point that describe this intersecting line. So finally, we're just going to construct the intersecting line. So step number 6, right? So the line just equals to 2 minus 1, 0 plus your parameterization variable t times your direction vector, which we have found before right here, 4 minus 1 and minus 3. Okay, so and then if you want to turn it into a parameterization form of the line, right, that's just going to be L equals to x equals to, right, x equals to 2 plus 4t, and then y equals to minus 1 plus minus t, right? And then z equals to 0 minus 3t. And then that should be the answer to this question. And that is answer choice B. All right, let's take a look at a second type of problem. And this is an easier one. A line L passes through points A and B, and at what point does the line intersect the xy plane? Okay, so this is a type of question of intersection of a line and a plane. Okay, the key word here is just that it's asking the intersection of a line and the plane, right? It's not the intersection of plane and the plane anymore. It's the intersection of line and the plane. Okay, so line and the plane. Okay, so the first step that we're gonna do is to find the vector from 2 points. Okay, from 2 points. This is not z. This is 2 points. So first we have, right. So we can find out a vector by finding the AB vector, right? So a vector AB is the vector. V equals to AB equals to B point minus A point equals to 2, 3, 1 minus 1 minus 2, 1. Okay, and this equals to 1, 5 minus 2. So, and the second thing that we can do is to find a point on the line, right? So, well, what in this question, right? The points are actually quite easy to find, right? We can just pick point A or B because they're already on the line, right? They consist the line themselves. Already on the line. Okay, so step 3, we're going to construct a line equation. Okay, so we're going to construct the line equation. Equals to L equals to A plus VT, and this will give us x equals to 1 plus 1t, y equals to minus 2 plus 5t, and then z equals to 1 minus 2t. Okay, so we have step 3, and then so that's step 3, and step 4 is what I call not plug the points, plug the line. Okay, plug the line into the plane. So what do I mean by that? Let's take a look at this example, right? So So this is the xy plane. So that means that means z equals to 0, right? And this is the equation of the plane. So what I mean by plug the line into the plane is that we have these x, y, z coordinate variables of the line. So whenever I see z, I am in my plane equation of the plane, I'm going to plug the equation of the z component of the line into the plane. So since we only have z in our plane equation, we're just going to plug in this into the plane. So that what we'll have is z of t equals to 1 minus 2t equals to 0, right? So this is how we're going to solve the problem. But let's just practice the concept a little bit, right? Let's say we have the same line equation. What if I have a different plane, right? Let's just say x minus 2y plus 3z equals to 1. Right, so what we're going to do is, right, we have x is 1 plus 1t, 1 plus 1t, and then minus 2 times y is minus 2 plus 5t, and then plus 3, 1 minus 2t equals to 1, right? And you can take, basically what I'm trying to illustrate that is this can be applied to planes that's not only to the xy plane, xz plane, and yz plane, right? You can apply to this concept can be applied to any plane. So we solve this equation, right? And then we solve for t, and then so step 5, we solve for t. We're just gonna have t equals to 1/2, right? I think that's a very easy equation to solve, right? And then we're gonna move on to step 6. We're just going to plug in the t that we just solved for to get the remaining coordinates of the intersection location. So step 6, right? We're gonna have x equal to 1 plus, right? This is the equation of the equation of the line is right here. So 1 plus 1 t, so t is 1/2, equals to 3 over 2, and then y equals to negative 2 plus 5 times 1/2 equals to 1 over 2, and then z is just simply 0. So this is the location of the intersection point. Right, so 3 over 2, 1 over 2, 0. Right, and if we go back to the problem, and then that is clearly the answer E.